Welcome. In the last module, we took a look at the partitioning process in physical design automation. In this module, we will take a look at floor planning and routing. At the output of the partitioning phase, we have a set of blocks defined because we have divided the circuit into a set of sub-circuits, each being called a block here. We know the area of the block. We at least have an estimate of the area of the block because we know the circuit components that will go inside a block and how they will be interconnected, and hence we have an estimate of the area of the block. We also know the possible shapes of each block and the number of terminals in each block because we know how many wires will cross the partition of a given partition, how many wires will cross the given partition and go to other partitions, and hence we know how many terminals that I will require because external connections across a partition can only be done through terminals at the periphery of each block, and we have a netlist specifying the connections between blocks. And we consider two types of blocks here: a fixed block. A layout of a circuit within a block is known, hence fixed dimension. So, if the complete layout of the circuit within a block is known, it is pre-designed, then the block is fixed or rigid. And flexible block, where the exact dimensions are not yet determined. We have an estimate of the area, but the exact dimensions had not yet been determined, and hence their aspect ratios and sizes can be changed within a given bound. Then what do we do at the floor planning phase? The input to the floor planning phase therefore is a set of blocks, both fixed and flexible. The area of each fixed block, the area of each block AI equals to Wi cross Hi is known, width cross height. The constraint on the shape of each block, rigid slash flexible, is known. The pin locations of the fixed blocks, the terminals, the locations of the terminals are known, and we know the interconnection among blocks as the netlist. What do we require? We require to find locations of each block so that no two blocks overlap. So, we want to obtain a relative placement of the blocks with respect to each other so that none of them overlap. Okay. So, what is the objective? The objective is to minimize the total area of the layout on the chip and to reduce the net length for critical nets. So, we can, if we place two blocks which have a high high amount of interconnection among them, far apart from each other, there will be a lot of wires through the chip area, long wires through the chip, through the routing area of the chip, connecting them, and hence it will lead to a loss in the area that we can obtain. It will lead to a reduction. It will lead to a loss in the reduction that we can possibly achieve in the area of the chip. We also want to reduce the net length for critical nets. Let us say that we have a net whose length cannot be more than a fixed length, some k nanometers. And why? Because if the net length is more than this, then my delay, the propagation delay through the wire will be such that the delay constraint for the signal which will pass through this wire will be violated, and hence we need to reduce the net length for critical nets. Critical length nets are what? They are the nets which take the highest amount of which are the longest nets, and hence the signals take the highest amount of time to propagate through them, and the performance of the chip is often determined by the length of these critical nets. Okay. An additional requirement of the floor planning phase is also to freeze the shapes of flexible blocks. So we have flexible blocks, we do the floor planning and then we freeze the shapes of the flexible blocks. How do we estimate the quality of a floor plan? The quality of a floor plan is measured by several different criteria. For example, minimize area, minimize total wire length, maximize routability, as we said, of the wires through the routing regions, the vacant spaces available on the floor of the chip. Now, to understand the floor planning problem and the solution approach, we will look at its ILP formulation. So, the problem is modeled as a set of linear equations using linear variables, and therefore an ILP. So, we are given a set of n blocks S equals to B1, B2 dot dot up to Bn, which are rigid and have fixed orientation, and each block is a 4 tuple. We know the left bottom corner of the we know the coordinates of the left bottom corner of the chip, we know the width of the chip, and we also know the height of the chip. Now, to ensure that any two blocks do not overlap, so now we need to determine what are the conditions that we need to ensure so that any two blocks Bi and Bj never overlap with each other. Now, let us say that we have two blocks Bi and Bj. Now, the first one is that, let us say that we have Xj to the right of Xi. If that is so, if Xj is to the right of Xi, then Xi plus Wi must be less than equals to Xj. To ensure that two blocks will never overlap, then we need to meet at least one of these 4 constraints here. So, what are they? Xi plus Wi less than Xj. If Xj or Bj is to the right of Bi. On the other hand, if Bj is on the top of Bi, then Yi plus Hi should be less than equals to Yj. If Bj is on the top of Bi. Third one, if Bj is on the left of Bi. So, Xi minus Wj has to be greater than equals to Xj. Why? Because Bj now is to the left of Bi. Now, if Bj is below Bi, then what happens? Yi minus Hj has to be greater than or equal to Yj. So, these 4 constraints need to be ensured to hold in. So, at least one of these 4 constraints need to hold to ensure that no two blocks Bi and Bj will ever overlap. Now, to obtain the set of constraints, we define 2 0 1 variables Xij and Yij for each vertex pair. For each vertex pair Bi Bj, we define 2 0 1 variables Xij and Yij. Now, Xij comma Yij equals to 0 0 if Bi is to the left of Bj. That is, if the first constraint Xi plus Wi less than equals to Xj, this is what we need to ensure, right? We will keep Xij comma Yij equals to 0 0. Xij Yij equals to 1 0 if Bi is below Bj. Xij Yij is 1 0 if Bi is to the right of Bj, and Xij Yij is 1 1 if Bi is above Bj, right? And let W be the sum of the widths of all the blocks that we have, and capital H be the summation. Let W be let summation Wi, let W equals to summation Wi be the summation of the widths of all the blocks that we have, and H equals to summation Hi be the summation of all the heights of the blocks that we have. Now, we write the constraints between any two pairs of vertices as follows. For each pair Bi, Bj, we need to have xi minus xj less than equals to w. So, they must be separated, they must be separate, their left coordinates must be separated by less than equals to w. Similarly, yi minus yj less than equals to capital H, the summation of the height. So, how far they can be apart? It can be the summation of the heights, right. So, these are trivial constraints which will always need to be satisfied. Now, how do we write the other four overlapping constraints? We said that at least one of the constraints need to be true. So, in our constraints, one of the constraint has to be true and the other constraints need to be trivially true. We will see how we will achieve this. So, xi plus wi less than xj plus capital W into xij plus yij. We said that when xj is on the right of xi, then what happens? Then xij comma yij equals to 0 0, right. So, if xi plus wi is less than equals to xj, if this is true, and this is what we want, that we want bj to be on the right of bi. If you want bj to be on the right of bi, then we want this constraint xi plus wi less than equals to xj to be true, and it should not be trivially true. And see that this is what happens here. If this is what we want, that bj should be on the right of bi, then xij plus yij is 0 0, and hence w into xij plus yij is also 0. So, this will not be trivially true. However, for the others, you see that all the other constraints will be trivially true. Why? Xij minus yij is 0 minus 0 is 0. So, h into 1, so h is there. So, for the yi plus hi less than equals to yj plus h will always be trivially true, right. Let us in the third constraint, because xij and yij are both 0, w will be there. So, xi minus capital W will not be equals to 0. So, capital W into 1 minus xij plus yij will not be 0. Therefore, xi minus wj greater than equals to xj minus capital W will be trivially true. Similarly, for the fourth constraint, yi minus hj will be greater than equals to yj minus 2h will be trivially true. Likewise, we will see that one of the constraints, depending on what we want a block to be placed on top of one, on top of the other, on the right of the other, below the other, or to the right of the other. Based on that, one of these constraints will be has to be non-trivially true. We have to make it true. The other constraints will be trivially true. And if any one of these constraints are satisfied, we know that these two blocks will never overlap, right. With this understanding, we come to the mathematical formulation of the ILP for floor planning. Let us assume that our objective is to minimize the height y of the floor plan. So, what will be the final formulation then? We have to minimize y, the height of the floor plan, subject to xi plus wi less than equal to capital W. So, where can W be placed farthest on the right of the chip? Such that xi plus wi, after the width, the block should be wholly placed within the area of the chip, and for that xi plus wi less than equals to capital W needs to be true. Yi plus hi less than equals to y. So, y is what we want to minimize. So, yi plus hi. So, where can a block be placed maximum on on the top part of the chip, we have to satisfy the constraint yi plus hi less than equals to capital Y. Also, we saw these other two constraints, xi minus xj less than equals to w and yi minus yj less than equals to h. And then we satisfy all these four constraints that we just mentioned in the last slide. One of these constraints will be true depending on the relative position of one block with respect to others, and it has to be true for all pairs of blocks, and therefore for all yij pairs these constraints have to be jotted down, and then we will feed this to an ILP solver, and the output will be an optimal solution with respect to the constraints that we have. The last constraint of course is that xi and yi both have to be greater than 0, right. The coordinates have to be greater than 0. So, with this we understand a mathematical formulation for the floor planning problem. With this we understand the ILP formulation for the floor planning problem. With this understanding, we will now move to the routing problem in physical design automation. The problem of routing is as follows. Given a floor planning and placement and a fixed number of metal layers, we need to find a valid pattern of horizontal and vertical wires that connect the terminals of the nets. So, we have the placed blocks, their exact positions known, and we know which wires will be interconnected between these blocks. So, in the routing phase, we need to find actual Manhattan paths through the vacant spaces within the blocks to connect these terminals. And what are the objectives? We may need, or we may want to minimize the routing area. We may want to minimize the area required for routing, so that the total area of the chip finally will be minimized. Now, routing is abstracted at two different levels. One is the global routing, the other is detailed routing. So, what is global routing? In the global routing, the input is the detailed placement after the floor planning and placement phase with exact terminal locations known. So, we know the exact terminal locations of the blocks. Now, we determine channels for each net. So, we determine the channels for each net. So, these are the channels. These are the channels. These are the empty regions, the channels between the blocks through which these these wires have to be routed. So, determine channel or routing region for each net, but we don't find out, we don't deal with where exactly within this channel my wire will be placed. So, which track within this channel is through which my wire will be placed, I don't determine in the global routing phase. I only find an enumeration of the channels through which my wire, a wire between any two terminals should pass. For example, let us say if we consider this net. If we consider this net, we found that it should go through this channel and then this channel and then this one here, right. So, this is the position it should take. There could be other more complicated ways in which you route a particular net. So, the objective is to minimize area or minimize congestion. So, we need to balance, we have a total routing area, different regions, and we need to balance the congestion within each of the different routing regions, that we have, and we want to minimize the congestion in these areas, so that the overall area of the routing region will be minimized. So, it is to minimize area or congestion and timing. Now, what we do in the detailed routing phase? In the detailed routing phase, we do the routing for each channel. Now at the global routing, after the global routing phase, we have known what are the wires that will pass through a given channel. So input channels and approximate routing from the global routing phase. So determine the exact route and layers for each net. So through which route and through which layer will these wires pass, right? Will these wires pass is found out in the detailed routing phase. So we take each channel at a time. From the global routing phase, we know what are the wires that will pass through this channel, and then we find an exact track for each of these wires. The objective is to obtain a valid routing, minimize area, meet timing constraints, etc. Additional objectives could be minimize vias. Vias are the connections between two distinct layers on a chip. So we have different layers on which the chip is designed. We have abstracted the chip as a single layer, but there can be multiple layers, and there are connections between layers. These connections are called vias, and routing or wiring is typically done through metal layers. So there are metal layers and polysilicon layers, and through which wiring can be done, and the connection between these layers are called vias. And one of the objectives of routing could be to minimize the number of vias. Now we take a look at a distinct routing type. Now we take a look at a distinct type of routing called grid routing. It comes within the global routing phase. The layout surface is assumed to be made up of a rectangular array of grid cells. Some of the grid cells act as obstacles, which are basically circuit blocks that are placed on the surface, and some nets that are already laid out. So we will now understand a specific global routing strategy called grid routing. So in the grid routing, the layout surface is assumed to be made up of a rectangular array of grid cells. Some of these grid cells act as obstacles. So what could be the obstacles? They could be blocks that are placed on the surface, or they could be some net that are already laid out. So now we want to lay a new net. We cannot bypass, or we cannot cross these nets, because it will create an electrical short, and we cannot cross through the blocks because those are circuit blocks. So the remaining vacant space, we have to do the routing through the remaining vacant space available. So what is the objective? Objective is to find out a path, a sequence of grid cells, that is for connecting two points belonging to the same net. We do this through Lee's algorithm. So one of the important grid routing algorithms is the Lee's algorithm. What are the characteristics of the Lee's algorithm? Lee's algorithm, with respect to the grid that we have, produces an optimal strategy. So what do we mean? If a path exists between a pair of points S and Y for two terminal nets, it produces an optimal strategy. If a path exists between a pair of points S and T, it is definitely found. It always finds the shortest path, and it basically uses depth first search. The time complexities are big O of n square for a grid of dimension n cross n. So what do we have in grid routing? We assume the floor of the chip to be as a grid. We assume the floor of the chip to be a grid. A grid consisting of n columns, n vertical wires. So we in grid routing, we assume the floor of the chip to be composed of a grid. The grid has n vertical wires and n horizontal wires in an n cross n grid, right? So one of the important grid routing algorithms is Lee's algorithm. In this algorithm, we basically do a breadth first search to find a path between two terminals, To find a route between two terminals, if a path exists between a pair of points S and T, it is definitely found, and it always finds the shortest path. These are its two properties. There are three phases to the Lee's algorithm. In the first phase, we say this to be the wave propagation phase. It's an iterative process. During step I, non-blocking grid cells at Manhattan distance I from grid cell S. S is the source and T is the target. So, at step I, non-blocking grid cells at Manhattan distance I from grid cell S are all labeled with I. Labeling continues until the target grid cell T is marked in step L. So, labeling continues until the target is reached. L is the length of the shortest path. So, let us take an example and see. In this example, we see that here is the source S. Here is the source S. Now, in the first, we said that there is a wave propagation, breadth first search, and it happens in iterations. In the first step, so if you go to the algorithm, in step I, non-blocking grid cells at Manhattan distance I from the grid cell S are all labeled with I. So, we see that in step 1, from this cell is at Manhattan distance 1 from S, this one is at Manhattan distance 1 from S, this one is also at Manhattan distance 1 from S, and hence these are labeled with 1. If you see this 2 is at Manhattan distance 2 from S, this is also at Manhattan distance 2 from S, this is also at Manhattan distance 2 from S, this is also at Manhattan distance 2 from S. Likewise, we go on propagating a wave, right? And at each level I, we label cells with the number I for to understand, to denote that these cells are at distance Manhattan distance I from the source S, and we go on doing this until the target is found. For this case, our target is at this position, and we see that it is found in the 8th step. After 7 we come to 8, so it is at a distance 8 from the source. So, again it is an iterative process. During step I, non-blocking grid cells at Manhattan distance I from grid cell S are all labeled with I. Labeling continues until the target grid cell T is marked in step L. L is the length of the shortest path. The process fails if T is not reached and no new grid cells can be labeled during step I. T is not reached, so when do we fail? When does the Lee's algorithm fail? T cannot be reached and no new grid cells can be labeled. Because it's a breadth first search, it will do an exhaustive search, and if the target is not there, then it will not be able to find, because let us say the target is at a place where it is surrounded on all sides by an obstacle. If it is not found surrounded by all sides by an obstacle, Lee's algorithm is bound to find it, right? However, there is another case in which Lee's algorithm can fail. If we bound the number of steps through which the iteration can progress to at most m, so T is not reached and equals m, so we cannot do a breadth first search beyond iteration m, then that is some upper bound and we do not find a target T, then the process fails. However, if I do not have such an upper bound and there is at least one available path to the target, Lee's algorithm will always find it, because it's an exhaustive search through wave propagation using breadth first search. Now, the second phase is the retrace phase. So, we systematically backtrack from the target cell T towards the source S, right, backwards towards the source S. If T was reached in step I, then at least one grid cell adjacent to it will be labeled I minus 1 and so on. So, what happens is that so now after phase 1, we backtrack and go back to the source. So, for example, we can take this path. So, there is, if T is reached at step 8, let us say, then there will be at least one with a step value I minus 1, here 8 minus 1. So we have a 7 here. So we could take any one of them. Let us say we take this one, and we progressively go back to the source S. So we go back 7, 6, 5, 4, 3, 2, 1, 0, or we could take 7, 6, 5, 4, 3, 7, 6, 5, 4, 3, 2, 1, 0. So not this one, I have made a small mistake. So it will be 7, 6, 5, 4, 3, 2, 1, S. Right? It could be any other path rather. It could be this also, 7, 6, 5, 4, 3, 2, 1, S. Now all these paths have the same Manhattan distance. All are shortest paths. This is another important thing to note. So if T was reached during step I, then at least one grid cell adjacent to it will be labeled I minus 1 and so on. By tracing the numbered cells in decreasing order, we can reach S following the shortest path. There is a choice of cells that can be made in general. In practice, the rule of thumb is not to change direction of the retrace unless one has to do so. Why? Because this reduces the number of bends in the wires. Right? Now, therefore, although all have the same path, we will favor this path, for example, and this path against this path. Right? We will favor this path and this path against this path. Okay. So this was the second phase of the Lee's algorithm. In the third phase of the Lee's algorithm, what do we have? In the third phase of the Lee's algorithm, we clear the labels that we created, the redundant labels that we created. All labeled cells except those corresponding to the path just found are cleared. The search complexity for this clearing process obviously is the same as the wave propagation itself, because if that was a wave propagation, and this will also be another wave propagation, to find out all cells which I have labeled in this path to provide a connection between these two terminals in this two terminal net. Only thing that in this clearance phase, we have to keep the path that we have chosen in phase 2 and delete all other steps, so that I can further progress the algorithm for another two terminal net. With this small introduction to routing, we come to the end of this module.